My name is Emilia Janisz. I am the Director of Strategy of the European Nuclear Society. I have a great pleasure to welcome all of you on site and online to a special event of the European Nuclear Society, Nuclear for Space Exploration. Nuclear for Space Exploration, strengthening the EU innovation and technological leadership. With distinguished guests on site, at the stage, and together with you, we hope for an interactive debate on how to strengthen the EU capabilities for the space missions run by nuclear. So I would like to welcome first Jan Brazil, Director of Strategy from Czech Ministry of Industry and Trade, for his welcome address.
Hey, good morning, everyone. I'm really glad to see you here and also you online. I would like to welcome you to this event. It's about nuclear. Nuclear, as you know, is a big priority for the Czech Council presidency. We, as the landlocked country, have to rely on nuclear in the terms of energy supply. So the Czech Republic, and also we have the tradition of Czechoslovakia, we are quite experienced in the production of nuclear energy, but also in research and development. Currently, there are many research projects ongoing also in the energy field, in the energy production field. We are currently involved in the development of small modular reactors. So we have 3D design, which we are currently having at the university level and at the level of the research center in Czech. And the government currently is planning to update the state energy policy and will again rely on nuclear and renewables. But of course, nuclear is not just about the energy production, it's also about non-electrical applications. So during the Czech presidency, we would like to speak about the production of heat and hydrogen, and also medical isotopes. So we are preparing a conference in Prague ahead of the informal energy council on the 11th of October. And this will be dedicated to the production of heat and hydrogen and also small modular reactors. And then in November on the 10th and 11th, there will be the possibility to join the discussion in Prague during the set plan conference, and also in the 1 week there will be the European Nuclear Energy Forum also in Prague, which will discuss also the potential of research, human capacities, HR, in nuclear and also in research. And we will have also a discussion about the future of the production of medical isotopes in Europe. I'm really glad that we can today speak about the nuclear energy in space. It's something what is not so usual to speak about in Brussels. So we are happy that we can have this discussion. And the experience of the Czech science and research is in calculations, simulations. Of course, nowadays it lacks experiments. So I will be really glad to hear today what we can do in Europe, where is the expertise, what kind of analysis Europe and the European Commission can do, and maybe how to involve also European funding in the frame of Horizon Europe or the cooperation among member states. Yes, thank you very much that you joined today, and a good discussion. Thanks.
Thank you very much, Jan. I would like to invite to the stage now the ENS European Parliament, European Nuclear Society President, not the European Parliament yet, Professor Leon Cizej. The floor is yours.
So thank you very much. It's sometimes really funny how people anticipate the careers will change in the future. I'm probably more towards what one of my colleagues said last week in a conference when he was 50. I'm a little bit more than 50. He said that he's approaching the extension of life. That's more nuclear term. But anyhow, I'm really glad to welcome you all here at this nuclear for energy for space exploration event, and the subtitle is strengthening the European Union innovation and technology leadership. So dear colleagues, dear panelists, dear distinguished guests, let me first thank to the Czech Presidency of the Council of European Union and Ministry of Trade, Industry and Trade of the Czech Republic for co-organization of this event, and also to the Czech Permanent Representation for hosting this event. So I understand we are close to 200 here and online, which is really a nice, not number, but nice show of interest for nuclear in space. European Nuclear Society is a learned society. It brings together more than 12,000 professionals from the academic world, research centers, industry, regulatory authorities, and we promote the development of nuclear science and technology and the understanding of peaceful nuclear applications. We are around since 1975, and we are the largest society, nuclear society in Europe. We have many activities. One of them, important for today, is the High Scientific Council. It's a kind of a think tank, people who think about situation, try to predict the future as far as it goes, or at least the trends in the future. And it's composed of 22 high reputable scientists from 16 European countries. The president, Dr. Eric Proust, is today with us. What is also important is that today we actually publish a paper, position paper, derived and written by the High Scientific Council on the nuclear energy for space exploration. It was in the coffee table outside. I see that most of it disappeared, so I don't have to say that it's there because you have it already. Thank you very much for that. Now, two more points perhaps. Usually with the nuclear, people tend to forget that it's the huge energy density of nuclear which makes it very useful, especially for space applications and also for applications on Earth. So for space applications where you would like to see the minimum mass with the largest energy density going out, nuclear is nearly perfect, be it heat electric generators or be it nuclear reactors, call it micro today, for space propulsion or something like that. The same story goes on the Earth. While a lot of people talk about the energy efficiency and efficient use of energy, not very many people talk about efficient use of materials for energy, where again the nuclear is kind of the best in both, in the energy density and how little materials you actually need for the production of very large amounts of energy. And it's stable and it's usually reliable. Also in sometimes also in the war conditions we have now experienced, nuclear plants operate reasonably reliable. Now, the good thing of today is that, as I understand, it's the first time that the nuclear and space communities meet together in Europe and discuss a little bit how to cooperate. So if the goal is strengthening the European innovation and technological leadership, that's the way to go. I would say that nuclear in space and nuclear on Earth needs a steady and long-term support also of research, not only of the production. It's the to simplify the things, whatever is going today on the university will probably be in life in about 10 years. And if there is nothing going on today in the university, there are no nuclear or space departments around, you can expect the same will happen in real life in 10 years. So that's why we need a stable research environment and investments in both nuclear for space and nuclear for Earth. Anyhow, let me stop talking about things. We have a distinguished panel here who will tell you much more, and you will be teased to ask them questions at the end. I'm looking forward to that. I wish you all a very enjoyable and informative meeting. And with this, thank you for your attention.
Thank you very much, Professor Zizek. I saw a lot of nodding heads as you were saying about the research and academy that needs to work together, especially from Jan. I brought you something. This is a spacecraft. This is a very serious spacecraft that is run by my daughter, 2.5-year-old daughter, Karolina. She plays with it every evening in her bath. And I wanted to invite you all to the discussion on what capabilities we need on the European level to run this spacecraft, including by nuclear. So first of all, I would like to invite Chairman of the High Scientific Council of the European Nuclear Society, Eric Proust, exactly there is the pointer, to present its flagship position paper currently, Nuclear for Space Exploration. Eric.
Hello to everyone. First, it is my great pleasure to present to you on behalf of the highest scientific council of the European Nuclear Society the position paper we are releasing today on nuclear energy for space exploration. First, if it doesn't work, which is a little bit problematic. Okay. First, a few words. We will see how this works on the screen. A few words about the genesis of the paper. Okay. What prompted the highest scientific council to take stock of this subject, nuclear energy for space exploration, are three elements of context. First, the general public is not aware of the key role nuclear energy played and will continue to play in deep space exploration. Europe does not have any nuclear space power capabilities. It fully depends on foreign ones, in particular the US. And recently, the US, Russia, and China separately has taken initiative for the development of new space nuclear systems to meet new challenges. So in this context, the High Scientific Council had one questioning what about Europe and a concern the apparent lack of any similar initiatives in Europe like the one in the US, Russia, and China. So having taken stock of the subject, the High Scientific Council decided really the subject was a position paper with the purpose to highlight the strategic role, in fact, nuclear energy in playing in deep space exploration, to highlight the need to develop new space nuclear systems to meet the future challenges of space exploration, and to encourage European involvement in building space nuclear capabilities. Okay, so let me introduce you to the key, the main messages the position paper aims to convey. The first message is that nuclear power systems have enabled tremendous strides in humankind's exploration of space. What you are seeing on the slides are iconic missions which were indeed enabled by nuclear energy, which were powered by nuclear energy. From the Apollo lunar scientific experiments in the late 60s to New Horizon, the first spacecraft to explore Pluton and its moon Charon in 2015, or the car-sized rover Curiosity and Perseverance, which are exploring craters on Mars, through Galileo, the first spacecraft to have orbited another planet, which was Jupiter, or Cassini, which orbited Saturn for more than 14 years and was the first spacecraft to land a probe on the moon of an outer planet. It was Titan, the moon of Saturn. And of course, the iconic missions, Voyager 1 and 2, which after having explored Jupiter, Saturn, Uranus, and Neptune, are now left the heliosphere and continue to transmit valuable data for more than 44 years after their launch. So all these missions, all these scientific achievements were enabled by nuclear energy, were powered by radioisotope thermoelectric generators, or RTG, which was those thin cylinders you see on the slides. The principle of RTG, the heat released by the radioactive decay of a radioisotope is converted into electricity using an array of thermocouples, with the waste heat being radiated into space. Typical RTG weighs like the one on the New Horizons spacecraft, weighed 56 kilos and supplies 300 watt electric at the beginning of life. The reason why nuclear energy is a key for deep space exploration is that there is no practical alternative to nuclear for powering missions that are aiming at exploring space region where sunlight is too weak. You have to understand that in space, there are only two options that could supply sufficient amounts of energy over an extended period of time. There are solar photovoltaics and there are nuclear. In space, the launch costs are quite expensive, and the power sources being the heaviest piece of equipment in any spacecraft, there is a strong incentive to favor the energy source which offers the highest specific power, or in other terms, the highest power to mass ratio. Leon already stressed that nuclear is well known for its intrinsically high specific power. Solar photovoltaics, the specific power of solar photovoltaics depends on solar irradiance, which decreases as the square of the distance to the sun, which explain why nuclear energy, while RTG outperform solar panels plus battery when where the sun is too far away, that is beyond Mars, or when the sun is eclipsed or obscured for long periods, like on the moon, where the nights last 14 days, or on Mars, where you have dust storms that englobe the planet for weeks. I spoke of RTG. They have well served the first exploration area, and they will continue to be, I would say, of strategic need. But now, higher energy density nuclear fission systems are needed to enable a new class of more ambitious space missions, space exploration missions that are envisaged today for the coming decades. First, you have to keep in mind that current space-proven propulsion systems limit deep space exploration, robotic exploration. Just think of New Horizons with its 300 watt electric RTG and its chemical propulsion, which was only capable of a speedy flyby of Pluton and took over a year to send back to Earth what data it could collect. Just imagine what could have been learned if New Horizons has the propulsive capability to orbit Pluto and the power capability to use more powerful instruments and transmission equipment. But what is driving today higher space power and propulsion performance requirement is the opening of a new human exploration era. Unfortunately, I have no pointer to target that, but this new new era has really great ambitions. The first human mission to the lunar surface beginning in 2026. Permanent lunar exploitation targeted by 2030, by the end of this decade, opening the way to the first human mission on Mars around 2040. So we are very ambitious era which is opening with targets which are within, I would say, the next 2 decades. You have to understand that we are speaking of permanent lunar outpost, which will have to rely on in-situ resource utilization. And beyond, we are speaking of the extraction of local resources. This will require industrial scale, safe and robust, high energy density sources, implying nuclear fission sources. And this new area also presents a number of challenges in terms of transportation, in-space transportation and logistics, which will require advanced, thrust-efficient and reliable propulsion solution, which a nuclear fission system can offer. You may wonder what do this space fission system looks like, and what I'm talking about when I'm speaking of nuclear propulsion. But first, a nuclear fission power source, such as it just simply, I would say, consists like a source on the Earth. It consists of a nuclear microreactor with its radiation shield, the heat source, an energy conversion system which converts heat into electricity, and a radiator, which is a specificity of space systems, a radiator to radiate waste heat into space. So something which is rather, I would say, classical. In terms of propulsion, there are 2 possible ways to use nuclear to make a propulsion engine. Nuclear thermal propulsion, where propellant is heated at high temperature into a nuclear reactor and then ejected at very high velocity, compared to chemical propulsion. This offers a twice higher thrust efficiency at similar thrust levels, so opening the way to a lighter space transfer vehicle, larger payloads, or faster transit times to Mars, thus reducing the crew exposure to high-intensity space radiation. The other way to use nuclear for propulsion is nuclear electric propulsion. This is a system which adopts electric thrusters, which are powered by nuclear fission power source. Compared to nuclear thermal propulsion, it further increase the thrust efficiency of the engine by a factor of 3 to 5 compared to the nuclear thermal propulsion, but it has very low thrust. So it could enable a new class of deep space robotic missions. It presents synergies of development with solar electric propulsion, and when coupled with the chemical propulsive engines, it can make a single spacecraft capable of of human single trip to Mars. So having presented to you the various types of nuclear fission, space nuclear fission systems we are talking about, what is the status of the current knowledge on each of these systems, and what are the lead time and the prospect to meet the demand of the new human space exploration area. So first, a nuclear fission power system that could be used to support permanent outposts on the moon could be developed within a decade, which is good news, having in mind that we are aiming at 2030 for permanent lunar exploitation. Okay. Indeed, such space fission power systems are not new. The USSR has flown in low Earth orbit more than 30 space nuclear reactors of 2 to 3 kilowatt electrics. These date back to the 70s and 80s, and you have a picture on the left of such nuclear space reactors. And a decade later, the US developed a 100 kilowatt electric system, the SP-100, which unfortunately, for which the program was stopped before nuclear ground testing. Current development in the US include the development of kilopower, system scalable from 1 to 10 kilowatt electric, which was nuclear ground tested in 2018. And a few months ago, NASA jointly with DoD awarded contracts for the development of initial design concepts of 40 kilowatt electric fission surface power system that could be ready for launch within a decade for demonstration on the moon. So you see this still this target 1 decade ahead of us. Nuclear thermal propulsion engines now. There is no fundamental technology breakthrough to build them. But to design and deliver a nuclear thermal propulsion engine will require not only really good engineering, but also sustained commitment and substantial investment over the next 2 decades. So we need 2 decades to deliver the system. So we need not to wait to start. In the past, the USSR and the US devoted huge program to the development of such engines. And in particular, the US rover NAVA program achieved a TRL of 6, and the 3 experimental nuclear rocket engines, which were nuclear ground tested, are claimed to have demonstrated all the requirements needed for a lunar space transportation vehicle or for masked human exploration missions. Current development in the US include the DRACO project of the DoD, DRACO meaning demonstration rocket for agile cislunar operation, which targets full-scale in-orbit demonstration in 2026, which is objectively extraordinarily ambitious. And last year, NASA awarded contracts for reactor concepts of nuclear thermal propulsion. Now, space nuclear propulsion systems, they are nothing more than, I already mentioned, than space fission power systems coupled with electric thrusters. So, however, for space tug applications, cargo or manned mission to Mars, they too will require really good engineering and substantial commitment and substantial investment over at least 2 decades. It is just the same scale as nuclear thermal propulsion. because such application will require nuclear power source in a few megawatt electric range, which is one order of magnitude beyond what has been investigated in the past in the US, and will also require clusters of electric thrusters in the 100 kilowatt electric range, which is once more, one order of magnitude beyond demonstrated thrusters. Russia and China are currently developing such systems. Russia initiated in 2010 the development of a 1 megawatt electric nuclear power space tug, and they recently confirmed their plan to deliver it in orbit by the end of the decade, by 2030. And China recently disclosed an ongoing program for the development of a 1 megawatt electric class space nuclear reactor to help its mission to Moon and Mars. So you have now the context, the general context. So let's now address the key question: what about Europe? How should we position ourselves as a European in this context? You have to have in mind that Europe up to now does not have any own RTG capabilities. It had been fully dependent on. I am browsing. I cannot read the slides. They are too far away. So sorry for. I really. Okay. Europe has been totally dependent on cooperation with its foreign partners, in particular the US, for space exploration mission requiring RTGs, which has induced a self-limited approach of the European science community to propose only non-nuclear solutions. So this has limited its ability to contribute to the exploration of the solar system beyond Jupiter in particular, but not only. You may have heard of the ExoMars, the delay in the ExoMars mission. The ExoMars mission, which should have been launched in summer, is dependent on Russian radioisotope units. And this dependence and the geostrategic context has led to probably more than 6 years delay in the mission. This make further clear, if need be, the need for a European autonomy in space radioisotope technology. Okay, and there is currently an ESA proposal for the development of European devices for using radioisotope energy. This is clearly a first step toward this goal, and the High Scientific Council encourage the ESA member state to support it. But we were speaking of RTG. I mentioned that a new human exploration era is opening, requiring increased higher space power and propulsion performance requirement, meaning that the Europe need to look beyond RTGs. Doesn't work. Oh. Okay, I will leave it like that. So Europe needs to look beyond RTGs. You have to realize that transportation and energy are strategic for space exploration. There are two of the critical aspects of space exploration, and they are essential prerequisites for the generation of strategic benefits, innovation, inspiration, and strategic economic capabilities. So in this context, clearly the view of the High Scientific Council is that for Europe to retain its leadership position in space exploration in the decades to come, it should position itself on the development of space nuclear fission power sources and nuclear propulsion systems. Europe has everything it takes to meet the challenge. Europe has the nuclear and space R&D and industrial capabilities and expertise. It has a long tradition of excellence and internal collaboration within these two fields. So by mobilizing its world-renowned space and nuclear communities to meet the challenges, Europe can take really its rightful place in this endeavor alongside the major space powers. But this will be a long-term endeavor. And I mentioned space power systems, at least a decade to develop, nuclear propulsion system, probably 2 decades. So this will be a long-term endeavor. And for it to succeed, there will be the, I would say, sustained commitment of and substantial initial investment by European institutions will be crucial. And so this means that at the first step in this endeavor, we need first to build a long-term European nuclear in-space strategy that addresses both power and propulsion, and a strategy which needs to be robust, resilient, and affordable. The HSC, the High Scientific Council, acknowledged a few recent European initiatives in the EU and ESA, in particular on RTGs and nuclear propulsion, which are very first step toward this goal. So, of course, we are strongly encouraging them. But you have to understand that to deliver this long-term strategy will require developing strong scientific and technical exchanges and cooperation between the European space and nuclear communities, and such cooperation does not exist yet. So to conclude, there are some anomalies, but anyway, to conclude, the main messages were on the last 3 slides, so you should still have them in mind. But to remind the key facts, the strategic role of nuclear energy in space exploration. This was very clear in the past, and it will continue to be there in the future even more, and in particular beyond science, to generate economic benefits of, in particular, the exploitation of extraterrestrial resources. The second element of context is up to now a complete dependence of Europe on missions requiring radioisotope fueled systems, which are clearly limited the ability of Europe to for space exploration. And the third element of context, an ambitious human exploration era, human exploration missions that are calling for new space nuclear systems, which are being developed today by the 3 major players, space powers. So we are of the opinion that Europe must develop its own nuclear capabilities to remain a strategic player for space exploration in the decades to come. And as I just reminded, I just told you in the last slides, for this endeavor to succeed, there will be a crucial need for sustained commitment and substantial investments, first from the European institution, but also then from the industry, which will require giving, I would say, everybody a clear view of our long-term objectives, to build a long-term strategy which be affordable, robust, and resilience, and to build also the accompanying roadmap. And for that, it will be essential to develop strong and effective scientific and technical exchanges and cooperation between our nuclear and space communities. Such cooperation does not exist. And the European Nuclear Society and its High Scientific Council are eager to contribute. Thank you for your attention, and sorry for the bugs.
Thank you very much. With this panel, we hope to have a strong exchange of scientific comments to the paper. So I would like to first maybe present all the panelists to you. Daniel Freys, Project Leader for Space Power Applications, EU Joint Research Center. Andrzej Schwab, Head of Space Technologies and Applications Unit at Ministry of Transport of the Czech Republic. Professor Markus Landgraf, Exploration System Architect, European Space Agency. Brieux Spindler, a Product Owner Space Innovation Lab at Tractable. Professor Sarah Batut, Head of the Radiobiology Unit at CKCN. And Jan Fribor, Deputy Head, Department of Nuclear Reactors and Czech Technical University. You had also a chance to read the paper before the event today. So I would like to ask you for the first impressions, like 2 sentences on this paper, on the timing. Do we really have all the elements to meet the challenges in the EU?
Okay, so yeah, my name is Daniel Freys. I didn't say good morning, so but good morning. Yeah, reacting to the paper, I read the paper, and I think we as a JRC, we are very positive about it. I think it sends a strong and encouraging message for the development of the nuclear power systems for this technology. And I think we fully agree that this is a key enabling technology, which is not just a nice to have, but which is a technology which is needed to perform certain missions, especially if it comes to industrial applications and human exploration of space. And I also agree, or we also agree, that Europe has all the necessary requirements. We have a strong nuclear industry. We have a strong developed nuclear safety framework to develop this technology. And I think we should stronger engage in this. Thank you very much.
Thank you very much. Andrzej?
Thank you. And at first, thank you for a very nice presentation and for a very convincing presentation. I have read the paper, and I have to say, in spite of that, I'm not expert on nuclear energy. My background is on space. The paper is very clear. It's future-looking. It's ambitious, and it's about the role what Europe would like to play in the future in space exploration, because the energy is absolutely essential. If you have no energy, you have no space exploration.
I think I take that. Okay, thanks, and thanks, Eric, for involving me in the writing the paper. And because I wanted to make a good contribution, I discussed it a little bit with colleagues. And in the space community, we're always being asked, why space? Right. So this is always this question: shouldn't we solve the problems on planet Earth first, and then do space stuff? And I'm sure that some in the room have that question on their mind, in particular in times when the general political message is that we should focus on urgent things that are problematic. Let me say that while that is true, that there's important crisis around, we cannot stop exploring space today. If we did, we would put Europe in a very difficult situation, because space exploration today is what basically access to the moon in the 22nd century will be the same as access to the Suez Canal in the 20s. It is as bad as that in a sense. If we Europeans don't have a foothold on the moon and we're building that in the 21st century, we'll be probably in a very bad situation in the next century. And don't forget, 22% of the 21st century are already gone. So we space people think a bit in the future, and the paper is brilliant, but of course it's not in the scope of the paper to talk about why space exploration is so important for Europe. But I wanted to give that message too, that space is strategic. Space exploration is strategic for Europe. Nuclear power is strategic for space. And we have those capabilities in Europe built up through research, but also through industrial activities in nuclear that will enable us to play a role in this very important field. So that I think the paper brings it across very well. And it's not a request from a community for budget. It's really our feeling as a group that if we don't do this, we're going to be in trouble in the not too distant future as a global player. And we hope that the stakeholders are very aware of that and working towards finding solutions of us maintaining a global position in space exploration. Thanks.
Well, good morning, everyone. My name is Brieux Spindler from Tractebel. And of course, I concur with what Eric just presented. Of course, the initial axiom is why space, as Marcus said. Once you've said that, it's strategic for Europe to be a leader and to be a major player in space. Well, the rationale is quite straightforward. We need nuclear energy for various missions, whether it's moon habitat or science missions, etc. So, of course, I will be presenting later on the sort of position of the industry regarding this, but we are ready, basically, and and we are eager to contribute to this strategy and develop the technology. Thank you.
Thank you very much. Sarah Batou from the Belgian Nuclear Research Center. Maybe I'll take another perspective. I think it's definitely the paper is very, very important. It's important to bring it now, if it's not even too late. I think it's really the moment to bring this paper and to have these joint forces at the level of Europe. The capabilities, the knowledge, the expertise, the educational level in Europe is also excellent. The forces are there, and the intellectual forces are there as well to fulfill this engagement. And I really hope that the EU as well as ESA will also push forward, as well as the industry and the educational aspects, the universities and the research centers will move forward conjointly to do that. I think also radiation, nuclear energy also has an important impact on the development, on technological development on Earth for production of energy, but also for understanding the impact of radiation on human health and developing potentially new opportunities like radiopharmaceuticals, like new shielding ways of protecting workers, of protecting patients, for improving really human healthcare in Europe and in the world. So I think there is really a good conjuncture now to push this forward. And I really would like to thank also the Czech Republic and the Czech Presidency for taking this initiative of organizing this first workshop together with the European Nuclear Society. I think it's really an important moment now that we are living. I'm very happy to be here today. Thank you.
Good morning, everyone. My name is Jan Freeboard. I'm presenting here on behalf of the university, Czech University. So therefore, I would also like to focus more on students, academia, and research done at universities. So I'm really glad that this topic is opening right now, because it's really the highest time to start with this kind of projects for space exploration and nuclear use for space exploration. And we need to think about those incentives, how to activate the research on all levels, like in universities. So really, research centers, universities, private companies, all they have to believe that this is a, let's say, viable direction of research. So they will need to invest their resources into this kind of research. So that's one thing we need to think about, how to activate, let's say, all levels of research and development in Europe.
Yeah, the variety of the panelists represent all possible actors that should be involved in this discussion. But maybe you have first impressions of the position paper. I know that you didn't have a chance to read it, the 15 pages, but maybe from the PowerPoint which was presented by Eric, 2 sentences. Someone from the audience? Yes, but 2 sentences. Yeah, because you will be not heard by the online participants, please.
Thank you. Well, congratulations for the excellent presentation, and hello to everyone. Yes, 2 sentences about the use of nuclear power in space. One is that it's not only for space applications, well, for space exploration, it's for many space applications. That includes radar satellites, observation satellites, are now high-power telecommunications satellites. It's almost everywhere that they are needed, and they are already applied in most of the military satellites they developed in the United States, in Russia, and now in China for many years. The other aspect, and it would be interesting to put that in the disposition paper, is the spin-off of these space technologies for Earth technologies. And I mean in crisis areas. I've been working, my name is Roland Goebel, I've been working in the ESA projects for many years, including the BeLife project, which was the integration of medical capacity with space applications, which could be deployed anywhere in crisis area. And during floods, during earthquakes, we can see that everywhere power can be known. And one of the best solutions would be not to have generators requiring fuel, because there is no fuel in this situation usually. It's to use thermoelectric generators or small fission reactors to cover the needs in crisis situation. And already the United States are beginning to developing that. And the major point is that in Europe, indeed, we need European strategic autonomy for that. Thank you.
Thank you very much. We heard a lot that we are dependent on the on other countries, on other regions of the world. But I would like to hear what is the current state of art of the European level from Daniel Freys. I would like to invite you to your slides. Would you like to? Okay. As you wish.
Short, let's say, overview of what happens in Europe. As I said, my name is Daniel Freys. I work for the European Commission's Joint Research Center. We are the scientific service of the European Commission, and we provide the policy DGs with scientific evidence for the whole policy cycle. And we have about 3,000 employees, people which work on, I think, in 5 different countries. And we are a DG of the European Commission. Yeah, it was already said that nuclear power systems, so NPS stands for nuclear power systems, are a key enabling technology. And I think this is a very central point that certain research missions, for instance, if you are far away from the sunlight, which was already said, let's say a bit beyond the orbit of Jupiter, it's simply not enough sunlight available to perform a research mission. So you need radioisotope or generally nuclear power. And especially if you get into the need for higher energy levels. So we speak about kilowatts, tens of kilowatts, hundreds of kilowatts, which are needed for human exploitation of space, for human exploitation of the moon, of the Mars, then it really comes into the situation that nuclear power and nuclear fission power will probably be needed in the future. This also is a key important aspect in the current situation where the European autonomy becomes more and more important. And it was also an aspect which was emphasized by President von der Leyen in the State of the Union a few days ago. So to develop this technology in Europe is one of the surely a priority of the European Union in the future. Just to give a short introduction about nuclear power systems, I think I can make it very short here. We have essentially two different types of nuclear power systems. And in Europe at the moment, we are pursuing three different ways or paths to develop nuclear power systems. The first type is based on radioisotope power, so the decay of a radioactive substance. Usually that's plutonium-238. It can be also americium-241 and others, but these two are the main nuclides which are pursued at the moment worldwide. And they provide up to several hundred watts of electric power by converting the heat released by the radioisotope into electricity with static or dynamic conversion systems. So up to now, only static systems, so Seebeck effect using thermocouples were used, which means it has a relatively low efficiency, only about 5%, but they are extremely reliable. So Voyager, which was presented before, for instance, is in space operation for about 50 years, still sending signals. However, if a dynamic conversion system could be developed to be reliable over a decade, or let's say 2 decades, then this would significantly improve the technology because you just need much less of the radioisotope. This third technology, or the second technology, is fission reactors. This is something which the development in Europe, let's say, is under discussion, has started. Of course, it's based on a broad range of historical knowledge and applications, and which was, you see here a picture of the Erato reactor, which was developed in France in the 1980s, I think, and also international experience. And it's certainly a well-proven technology because we are operating with 180 nuclear reactors in Europe. But for space, it has certain requirements to be sent into space, so it really needs some commitment to develop that. And I think here we are more at the beginning. It's more a medium-term technology, while the realization of the radioisotope power systems is something which could be called a more near-term option, let's say. The European framework, as I said, we have a strong space industry and own launch capacities. For instance, here you can see the Space Center in French Guiana. We have a strong nuclear industry and research infrastructure. We have qualified human resources and an excellent academic environment for nuclear. We have a well-established nuclear regulatory framework. And something which should not be underestimated, in my opinion, is in Europe, we have a high safety culture. We are committed to ethic principles, public participation and transparency. And this means who else, if not we, should go into this technology, to do this technology. And we also have a fully developed nuclear fuel cycle, which means we have a lot of synergies with the existing industry and an established reprocessing industry, which is already a basic cornerstone to divide the radioisotopes or to provide the radioisotopes. For instance, the americium-241, which is being developed as one of the technology paths at the moment, can be separated from the existing plutonium stocks in the large European reprocessing facilities. And the plutonium-238, there we have powerful research reactors in Europe, which can be used to produce this plutonium-238. So from my point of view, I think these two different technologies, americium-241 and plutonium-238, they are kind of complementary for different applications. If I have time, I can perhaps get into that a bit later. And I think we should pursue both. And for sure, we should also pursue the development of fission reactors. The European technology development, this is what's currently ongoing. As I said, we have the development of americium-241 based RHU and RTG. RHU is radioisotope heater unit. This means that you don't have the conversion into electricity. You just provide the heat to keep the sensitive electronics of the spacecraft at a minimum temperature which is needed. For instance, if you want to operate a rover on the surface of the moon and you have a lunar night of 14 days, in order to survive this cold environment, this needs to be kept at a minimum temperature. It's a very simple and convenient way to provide this heat. And then, of course, there are the RTGs, which convert the electricity into the heat into electricity. Currently, this technology is on technology readiness level 4. Involved organizations in Europe are the University of Leicester, which is coordinating this or leading this effort, then the National Nuclear Laboratory, Arianespace. We are also involved from JRC side and others. The development of plutonium-238 based RPS was with dynamic conversion was recently launched with the Horizon Euratom project Pulsar, which is led by Tractebel. So I think Brieux will speak about that in more detail. Partners here are the SCK-CN, which have the BR2 reactor in Belgium, a very powerful reactor capable to produce plutonium-238. The CEA, the French Atomic Energy Commission, Airbus, JRC, and others. And it was kicked off essentially by a feasibility study, which was funded by ESA, and where Tractebel and SCK already investigated the possibility of the plutonium-238 production in Europe. And now, as I said, the Horizon Euratom project Pulsar was just started, funded by the European Commission. So this is something where the European Commission can contribute to the development of this technology by funding research projects, for instance. So, and the expectation here is that we have a full-scale production potentially of plutonium-238 and a flight-ready system by around 2035. And then the third action is, which is under discussion at the moment, the initiative for microreactors in space. And as I said, this is a starting point, but I think we really have to go into this development as well. Yeah, one of the two, let's say, major frameworks or major cornerstones which have to be developed, in our opinion, to make this a success. So not only to recognize that it's a fantastic technology, I think we all agree on that, but to say what can we do that it really becomes reality, is the development of a European safety framework. This is under development currently, and on this slide you can see a bit the international framework documents which are already existing, the European framework documents which are already existing, and the French framework. Because if you want to launch a nuclear power system into space as autonomous Europe, then you will have to do it from French territory, which means that the French authorities are responsible for the licensing process. This will be the ENS, now ASN, the Autorité de Sûreté Nucléaire, for the ground operations, and the Centre National d'Études Spatiales for the launch approval process. So, and I think this is a cornerstone which has to be developed. The expected nuclear safety documentation will then be preliminary risk assessment, preliminary nuclear safety file, and the final nuclear safety file. And these documentations will then come on top of the launch approval of the normal launch approval process, which is anyway performed by the CNNS. Here, of course, also from the European Commission, the Joint Research Center can support, but we don't have a direct role here. As I said, it's more providing a framework, providing assistance if required. Then the second thing is the development of the production capacity in Europe for the isotopes. I think this is really key. The isotopes are scarce. So plutonium-238 is used over the last decades, but the production in US has been, I think, stopped in the beginning of the 1990s. So now it's being re-established, but they will not have enough for themselves. So they will not be able to share with us. So if we want to have our own meaningful research missions in the future, we need to establish the production of the isotopes. And here, what we need to do is to assess the existing industrial and research infrastructure, because it makes large sense to use the synergies So not to to build things new which we already have. So, and there, for instance, this Americium 241 initiative is a good example. We used existing Americium from the reprocessing facility to produce nuclear power sources, and also the plutonium 238 initiative, where we used the existing infrastructure to establish a supply chain here. And here the European Commission supports via Euratom funding and JRC actions. So also from JRC side, we are directly involved in the development of the nuclear fuel. So for instance, in the frame of the Pulsar project, we are developing the pellet production capacity at our institute in Karlsruhe. Then the second one is the development of a standardized heat source architecture. And from my opinion, I think this is a very important step to make it real, not to develop the heat source with in view of a certain mission, but to develop a standardized generic design. So this is what you can see here. On the right side is the general purpose heat source of the US. And below you can see one of the typical pellets, plutonium 238 pellets, which is clad in iridium. So this is a general purpose heat source, which can be stacked on top of each other in order to meet the requirements of each mission. And it has an existing generic design, so which means that the licensing process for each mission is much simplified. It's a well-proven design, and that is something where I think should be the vision for Europe, to develop such a standardized design. And we should make use of existing and well-proven design principles for the safety design. So I think large improvements can be made by the dynamic conversion systems. So here we can really reduce the amount of plutonium 238 which is needed. But in order to make it a reality, we should not invent the wheel a second time. We should really look into what is existing, what is well proven, and make an evolutionary approach. And then, as I said, the third point from our point of view is the establishment of nuclear safety framework for space, where we have to define the legal and licensing framework, build up the technical competence in the regulatory authorities and in the technical support organizations. And yeah, this is the responsibility of the member states, but here we can provide assistance and framework documents to give it a European framework, essentially. Yeah, thank you very much.
Thank you very much, Daniel. I would like to invite immediately Andrei, because I know that you have to leave. You have a good excuse to leave us. Maybe you can say about the meeting of today, that why you have to run.
Yeah, so thank you at first. Maybe let me cross the barrier and be a bit closer to you, because I have no presentation. I have just a couple of words about the topic we are here talking about it today. It's about nuclear energy for space exploration. And as I already said on the very beginning, it's about the role what the Europe would like to play in space exploration. But what does it mean, space exploration? It's about exploration of the new worlds, and I have in mind the worlds in frame of the solar system. Yeah, not let's say the deep space missions, the really deep space missions, as for example for Star Trek are known. But anyway, so when we are talking about the moon, when we are talking about Mars, and about the orbit which is behind Jupiter, it's important to have some kind of power system, some kind of power supply. And it has been mentioned here on the presentations, and the excellent presentation in the very beginning, and in the presentation of our ESA colleague, that there is, GRC colleague, that there are just two possibilities which kind of energy we would be able to have. It's photoelectric energy, that means the solar panels, and it is about the nuclear power sources. So I think that the vision, what is important to have for the space exploration, and it covers also the mining in the asteroids. it's not only about the presence of the humans, for example, in the Mars or on the Moon, but it's about the robotics, about robotic exploration, about high powerful systems also in the orbit of the Earth, as it was already mentioned here, because in military is used in present days. So I believe that we would need to, because we do have a vision. I think it's clear that the vision is here. What for we need to use this kind of power systems, but what do we need as the future steps? It's I believe the metrics of needs. What do we really need to do to reach our visions? Then it's important to have the strategy, because we are talking about the technology which is critical but not operational yet here in Europe. Europe is fully dependent on the players in United States. We heard that there are the players in China, maybe in Russia, which are working on this kind of technology. And it's really the question if Europe would like to be dependent on this player in the future as well, or if we will start the discussion already now about the European autonomy in this field as well. What I think that this workshop and this discussion paper could be the good starter for this kind of discussion. So what is need for the future? As I said, to have the metrics of need, it's important to have the strategy, but also it's important to have the cooperation and the resources. So looking around, what kind of institutions and industry do we have here in Europe? Of course, it's the European Union, it's Horizon, so that means the framework is already here. And of course, here is also European Space Agency, which is working on the space exploration for a long time. So I believe that the common cooperation of the Union, of the Commission, of the European Space Agency, of the member states, what is very important, and of course of the industry is absolutely essential for success in this really ambitious project, to have the European nuclear power resource or source of the energy for space exploration. So from my perspective, from my point of view, as I said, I'm not the expert on the nuclear energy. My background is space. This is interesting and I believe important kickoff of the future discussions, which should be led in European level. So thank you for that. Thank you for your presentations. Thank you for your statements and of course for the position paper, which is very clear for me and it's very good or very well visible. What is the goal and what kind of future steps do we need? Maybe one more thing or one more point I already forget, it's harmonization. The safety was mentioned, but harmonization, I think, not yet. It's a very important point, and from my perspective, somebody who is already working on the harmonization, on technology harmonization, should deal with this. And it could be the European Space Agency in close cooperation with the players in nuclear energy field, let's say. So, and that's conclude my short statement. So thank you for the floor. Thank you for the invitation. Thank you for the paper, and thank you for being present here.
Yes, the timing of this event is really perfect because today is the meeting of the council of the attachés who are dealing with space as well. So Andre is running to the meeting, taking out maybe some conclusions of the meeting already. Thank you very much. So now I would like to invite Professor Landgraf for a short statement on behalf of ESA.
Thank you. Can I have the rocket?
Of course. Carolina said yes, so.
Okay, Carolina. Yeah, for me, thanks for the words that my previous speakers have made, and I will probably join them by a desperate call for action. I think that's what this is a desperate call for action for stakeholders to engage in nuclear power system in space. And for me, today is a little bit emotional day for two reasons. It's my son's 13th birthday, and which is more relevant here, is the day that the ExoMars mission should have launched today. 15 years of development, thousands of scientists, engineers in Europe have worked on it. Their careers depended on it. And it's still hanging on thread. And it's a very sad story. And we'll try to fix it in ESA, and my boss, David Parker, is working on that as we speak in Paris at the International Astronautical Congress. So this day is important, but I would like to talk about the future really. And I spoke about the strategic role of space exploration, which brings me to this rocket. This is the space shuttle, right, without the orbiter. And what makes this thing fly is really is propulsion and power. And both are potentially provided by nuclear. And this strategic role of space is again of space exploration is difficult to explain because we live in times where there's on the political level there's conservative forces that drive us towards deindustrialization. I would like to quote Elon Musk, who is one of the players now. He's not a democratically elected player in the space field, but he is a player because he's rich, which is a bit a shame, and that's not the European way. But he said something interesting still. He's an inspiring figure, and he said there are two futures for humankind. One in which we deindustrialize and starve billions of people because without the industry we cannot nourish them. Or the other one where we become an interplanetary species. And I think realistically speaking, we will not starve billions of people. We will become an interplanetary species. We will use the resources in the solar system. And like I said before, the moon today is what the Suez Canal was in the 20th century. Without access to the moon, we Europeans will not have the conduit, the bridgehead into the solar system to have access to those resources, which are energy, which are materials, which are innovation and inspiration. So that's my first point here, that we are strategic in Europe. The second point is the strategic role, and my previous speakers have shown it, what really technologically is behind the strategic role of nuclear technology in space exploration. To bring a little bit of human dimension into that, in our human spaceflight program, we're looking at actually operating with European astronauts on the lunar surface. Just imagine you're operating on the moon in a habitat in a science laboratory. Something goes wrong, the sun sets, something goes wrong, and your battery doesn't have the capacity that it was supposed to have. Like, you know, from your car, when you start it in the morning, sometimes the battery doesn't do what it's supposed to do. That is basically a death sentence, because you're going to starve slowly, because it gets colder, and you're going to die slowly because it's getting colder. Because it's getting colder, the battery gets even worse, because batteries don't work well when they're getting cold. Your electronics fail, your life support systems fail, and you die. And that's why, and the moon rises, but 14 days later on your cold dead body. So okay, I'm sorry for that, but it's bad as that. It is, and then robots are not better. You know, if you told, yeah, robots can do that thing, but they cannot. If I put my iPhone on the moon at night, it dies after an hour, after the sunset. So they are sensitive too. We will not explore the solar system without nuclear technology, and it's been made abundantly clear in the paper and by Eric and by Andrei and by Daniel. So we'll not explore the solar system without nuclear technology. And people have tried, and we have actually made a mistake in Europe to constraining our scientists to propose non-nuclear missions, which has basically killed the outer solar system exploration community in Europe. And they went to the US, and they're now in Boulder, Colorado, which is sad. So my last point is that we have those competences in Europe, and everybody spoke about it. I'm sitting next to Brieux, who's been doing a brilliant study for us on plutonium-238, and within how many months? I don't know, 6? Yeah, 6 months. It would have been not possible if we didn't have the knowledge, the institutions, the facilities. Yeah. So, and that shows that we have it. And that's my final call to action, is a little bit personal. In ESA, we have the Council on Ministerial level in November in Paris, where we are proposing the ENDURE program. ENDURE is an acronym, and I can't remember which one it is. European Devices Utilizing radioisotope energy, right? That's ENDURE. And that program is up for subscription. It's 135 million over 6 years. So it's not a big program, but it's essential, strategic. So if you know your European Space Agency delegate, please talk to them about ENDURE and make sure that they understand the strategic importance of this program. And then we will work on that together with our industry and with academia to implement a good, safe space nuclear program. And that's my message, is basically to this audience. Thank you.
Thank you very much, Markus. Now I would like to invite Brieux for industrial answer to the challenges. And
perhaps the mic. Thank you. All right, quick quick table of content, but I'll jump immediately to a brief presentation of Tractebel, because perhaps some of you don't know Tractebel. Well, Tractebel is an engineering company, and we are active in the power sector, really. And in terms of nuclear, you see that we have a sort of critical mass of 1,000 FTE, full-time equivalent, whether that be scientists, engineers, technicians, and we are based a bit all around the world. It is a Belgian company headquartered here in Brussels, and so we, in terms of nuclear, we provide services, consultancy services, engineering services on the whole cycle of the nuclear activity, whether it's new build to providing services to operators of nuclear power plant in terms of safety and affordability, of course, up to the decommissioning of plants and the hard waste management. And also we are active in the new technologies, small, medium reactors, and also in the medical sector. And of course, now we couldn't miss to be part of this nuclear space exploration journey. So a bit of context, but this has been largely said by my predecessors. I mean, it's a new era of space exploration. 65 years ago, there was Sputnik. We don't want to live another Sputnik. That's really where we want to be. Once we've approved that space exploration is needed, then really sort of automatically we come to nuclear for powering missions. Next. Thank you. So quickly, because this is more things that haven't been said by my predecessors, or a bit by Daniel, of course. First of all, we need fuel. I mean, of course, an RTG is a very nice thing, but you need fuel. Fuel, either you have a couple of isotopes which are available. We've mentioned americium-241. Plutonium-238 is another possibility. And as a matter of fact, in Europe, we have the assets, industrial assets, to produce plutonium-238. So the idea behind that study is, why do we not take advantage of these assets to make this a reality? So together with partners, Orano, the operator, owner of the La Hague reprocessing plant, and SCK CEN, which is the operator of the R&D reactor, the BR2, a high flux neutron reactor. We embarked into this study, and as a matter of fact, yes, we have the technology, we have the knowledge. However, it is a long journey to produce and to have a significant amount of plutonium-238 at hand to be used in a nuclear device. So we did, with our colleagues from Orano and SCK, a full exercise regarding the technical feasibility. And of course, we evaluated the necessary financial means, whether it CapEx or OpEx, to that end. And basically, the conclusion was that it is feasible. It is feasible technically. There is no technological issue or barrier to that. We have the technical knowledge, and we have the industrial facilities to do that. Now, in terms of financial evaluations, we came up with a number which, when presented to Isa and to Marcus, confirmed that this is, of course, at the higher hand of the budgetary of a billion space mission. But since there was a lot of opportunities to reduce the cost of producing the plutonium, the conclusion was to say, well, it is favorable, it is interesting, and certainly, as we don't have the enough radioisotope to fuel all the missions ambitions that we have, we should pursue to fine-tune this and even go to a laboratory scale to make sure that we haven't missed in the value chain of producing the PU everything which needs to be considered. Voilà. So this is a transition, of course, to Pulsar, as mentioned by Daniel. Pulsar is a dynamic radioisotope power system, and you need fuel, of course, to use, because you need fuel to have the heat from the decay of the isotope. But here, instead of having thermocouples that exploit the Seebeck effect, you have a Stirling engine. So you have a dynamic engine that pushes, of course, the efficiency of the conversion from thermal to electricity. It's a much better system. From 5% efficiency, you can jump up to 25%. So the need for isotope is less to have a similar output in energy. And so that's the idea behind. And you see that we have key actors really in this project, whether it's the nuclear sector with, again, our usual suspect, SCK, le CEA, the European Commission with the GRC and Daniel, Airbus Defence and Space, Ariane, and two high-tech consultancies that would help us to look for other markets than space exploration. That was briefly mentioned. RTG in a disaster recovery mode or in submarine drones. RTGs could be, or RPS could be also interesting. Now we've just kickstarted the project, and the expectation is that we will reach TRL4 within 24 months. So that's very ambitious, but we feel that, as was Eric saying, there's no technological breakthrough. We think that a laboratory scale prototype is feasible within 2 years. Okay, important to say also is that we have created an advisory group with the key stakeholders, whether from ESA, and Marcus has accepted the invitation to sit on that board. The European Commission, of course, with Euratom representative and nuclear safety authorities. Key stakeholders will also be part of that advisory group, to which we will report. And this advisory group will help us also to focus on the areas of need for those key stakeholders. The first meeting is scheduled in the first quarter of 2023. Now, we've had the RPS with the fuel, and now a couple of words on the microreactor. As was said earlier, in order to fuel, well, there is a lot of ambitions, and we need a lot of power. There is this consortium in the US, which is called the Lunar Surface Innovation Consortium, which is organized under the auspices of NASA. And so it is a consortium regrouping industry from the US and looking at the of different aspects of colony on the moon, really. And there is a subgroup which deals with the power. And so they made all kinds of estimations and of the various missions that is needed. We've talked about the production of oxygen for propellant, a bit for life support, rover exploring the moon, etc. Science mission, COMSAT needs, and they came up with a need of 1 megawatt. Of course, the RTG of an RPS is not exactly what what is needed. Just like if you had one battery and you want to power a truck, that's not going to work. You need a reactor, obviously. And we in Europe, we don't have also the launch capacity of this Goliath SLS system. So if we look at the European launcher, the biggest one is a Ariane 6 4. The capacity is less. So of course, this has also a constraint on the size of the reactor. So we, you know, just as the saying said, you don't have oil, but you have ideas. We need to be more clever, and I think we are, you know, in some sense. You know, in Europe, there's a lot of intelligence, and you know, the fact that we are resource constraint make us more creative. And so what we think, of course, is to achieve this type of power with a modular. And this also fits well in the current mainstream R&D on SMR for terrestrial application. All right, okay, so we have federated around Tractebel a certain number of key players already. We have presented this to Marcus and to the European Commission, etc. Basically, we are ready to start activities. If there is, I think it's not just about, you know, a budget. I think it's about more the alignment of planet. You know, in the US, for some nuclear missions, the authorization is taken by the Oval Office. Okay, so it's a very direct decision from the president to the launch in Cap Canaveral. And so this is for us a challenge, of course, in Europe to align the planets. But I think the will is there. I mean, there is definitely, I feel, a consensus. The State of the Union speech by von der Leyen, the President von der Leyen, was really very inspiring about this. So anyway, we are ready. Industry is ready. That's it. So a couple of key takeaways. We have developed within those two or three initiatives. There are perhaps a foundation of what could be with the advisory board, for instance, and the technical expertise from various industry players from the space sector and the nuclear sector. There is a foundation of perhaps a core group that could serve and feed the development of this European strategy on the development of nuclear space capabilities. That's it for me. Thank you.
Much. We heard from industry, we are ready. So what about the research?
Okay. Thank you very much. I hope I have some slides. I hope that they can be put on the screen.
Yes. Okay.
Okay. It's coming. Yes, okay, thank you very much. So I'd like to bring a little bit the perspective of a scientist like myself. I'm a biologist by training, and I'm working in the field of space radiation for the past 20 years, and I've been very lucky in my institute at the Belgian Nuclear Research Center. We have been flying about 15 experiments so far to space. So most of the experiments that we've been flying have been taking place on the ISS, on the International Space Station, which is really a beautiful piece of equipment where a lot of scientists like me, like my team, but also all over the world and all over Europe are performing different tests in order to understand what is the impact of radiation on human health, on the astronauts, on the equipment, but also on life support. How can we provide food and the necessary necessities in terms of recycling urine, feces, producing water, producing pure water and oxygen for future endeavor to space. So these are really important issues that are tackled amongst others by scientists. So what I would like to bring also, if I may have the next slide, please. The next slide shows some of the latest, some of the first pictures that we have received that are absolutely inspiring. These are my favorite pictures from the James Webb telescope, the pillars of creation. And this is also where nuclear energy is very useful and important. This is very inspiring. Inspiring in terms of space exploration, is inspiring, innovative, is creative, and allows us to push forward the boundaries of knowledge and intellectual development of our species. So, but indeed, nuclear energy would be needed to continue to further explore space, cosmos, galaxies. I just would like also to say a few words about fission, about the sun, this energy producer that we have at our disposal, and the fact that on Earth we are trying to mimic this fission, this fusion, this sun fusion on Earth, and amongst others by a beautiful international project, the ITER project, in which amongst others a lot of partners have been working, and my institute in particular. So there is also an important feedback on Earth producing energy through understanding better how space energy is produced amongst others by the sun. Another point, if I may. Another point also of cross-fertilization, and we heard that we have the ministerial coming in a couple of months, where the Endure program will be presented. I think it's a very important and very strategic program for the ESA nations. But at the same time, we also have the start of the Pulsar project, and these are concomitant. And this is really a nice conjuncture that it's happening now, and that these things would not have happened 3 years ago. So these are really important stones, I think, in this in nuclear energy for space exploration. We are also together with different nations, with different international space agencies in harmony and aligned in terms of human space exploration programs. These are also quite recent for the past few years to really align to go around the moon, to go back on the moon, to stay on the moon for mankind, and then thereafter to go to the getaway to Mars. So this is a very important, very exciting, very innovative period of the Artemis program, and this is also a huge adventure that mankind is taking for the moment. But radiation is always present in the space environment. The space environment is very harsh for the equipment, harsh for mankind. So there is really a need, in parallel to all the development we've been talking about, to also protect better, protect astronauts, protect equipment, and develop also better dosimetry, better understanding of the space environment and the space radiation environment, in order to use all the potential in terms of understanding, protecting, characterizing, and also developing new tools that can be used on Earth, amongst others, shielding or new radiopharmaceuticals from our knowledge from the space radiation environment. So a lot of beautiful adventure which is taking place for the moment and for the next years, in which we are very lucky to take part. On Mars, we have Perseverance working with an RTG, which is very important. But I would like also to make taking a lot of information and bringing back on Earth a lot of information for science to develop. But let's not forget also, and I would like to give an example, as in Belgium at the BR2, we mentioned the BR2. In the 60s, we had radium, and we put it in the BR2, and we changed it, transformed it into actinium-227. So again, this actinium was not used for the RTG, but was used for other purposes, where again we have a cross-fertilization between RTG technologies and propulsion technologies with medicine. This actinium-227 is now used currently for palliative care for prostate cancer patients. So there is really a kind of integration and cross-fertilizations of the two fields in order to improve treatment on Earth for mankind. The International Space Station is operational. I hope it will continue to stay operational for numerous years, because for scientists like myself, it's really a huge and very important tool to be able to study different aspects that are related to nuclear energy. Amongst others, dosimetry. Our institute is very active into dosimetry for the past 20 years, understanding, characterizing dosimetry, the doses inside the ISS, inside a space vehicle, but also outside, and understanding also secondary particle production and generation from the type of space vehicle and the type of material which is used to protect a space vehicle for the future. So these are very important data that are now gathered on the ISS, but that are very important also for future mission to the moon and to Mars. Important also is to prepare mankind. We have a picture here of our astronaut Frank de Win that have been participating in our studies for the past 20 years and being a very big supporter of our research. We are following up astronauts that are spending 6 months to 1 year on the International Space Station. What does it give us? It helps us to understand radiation sensitivity. We are not all equal in terms of radiation sensitivity. Some patients, some astronauts are more sensitive than others. And it's important to develop future treatment that are better characterized and better taking into account this radiation susceptibility, radiation sensitivity, in order to adapt protocols of radiotherapy, of treatment for cancer or for other types of therapy, depending on the sensitivity of the patients. So this type of studies on astronauts is really crucial for future missions to the moon and to Mars. And for example, to decide, and we have for that an ESA topical team on personalized medicine that really help to understand and develop future programs for each astronaut, depending on their sensitivity towards radiation, but also sensitivity towards any kind of pharmaca that they will have to take, because any pharmaca could also have different types of impact on them in space. We are also working on life support. You see one of the first bioreactors that have been flying to the ISS in a very successful way a few years ago, which is part of the MELISA program, which is an ESA program for life support. Very important also to go to the moon and certainly to go to Mars. We will need a good life support system that are resistant against radiation, organisms that can help us to recycle and that help us, but that are also radiation resistant. Also, some biology studies that you see in the slides here showing rotifers. These are small organisms. This is a collaboration, international collaborations, but also with Belgium as centerpiece for that, where microorganisms and small organisms can really help in order to understand how we can build up and increase and improve radiation resistance of patients and of astronauts. And dosimetry, again, shown here, is very important. We also, the research on space and radiation is also interesting for understanding what happens if we use space analogs. There are space analogs on Earth where you can simulate part of the radiation spectrum, but there are also other space analogs that are very interesting also to understand the impact of space, the space context, which is not only radiation, microgravity, but also a lot of different stresses on the organisms. And one of these platform is Antarctica. And here you see one of the missions that we were very lucky to do on the Princess Elisabeth station, the Belgian station, a few years ago in order to monitor. It was a space project paid by Belspo and supported by ESA in order to understand better the impact on human health of prolonged stress and isolation. So let's not forget, going to the moon and to Mars really helps us to improve medical care, to improve resistance, adapt protocol to patients. So there is really an added value of all this type of research on Earth for improving mankind, on top of all the presentations that have been given by my predecessors. So thank you very much for your attention.
Synergies, and we will talk about the synergies on the terrestrial and the space use. But first, I would like to hear a representative of academia. How ready are you for the challenges ahead?
Thank you very much for invitation. Let's see if we can have those slides available. Yes, great. So once again, good morning. We have heard a lot of presentations here, interesting thoughts about the current state and the future, let's say, perspectives of this nuclear research for space exploration in Europe. I would like to share a few more ideas from the academic standpoint. Okay, so first of all, I would like to get to the next slide. Yes, there it is. So we have heard that in Europe, we have what is necessary for successful research and applications in this nuclear space exploration, but we definitely need to engage young people for this kind of research. So they need to feel that it's a reliable, clear alternative for their future careers. So they need to see that there will be application for their research. So they that's the position that everyone wants to see somehow the application of their research. And on the other hand, universities are able to do, let's say, a huge amount of research. And at universities, we are really, let's say, bold in this research. So we don't need to focus, let's say, on immediate applications. So we can
explore many different ideas. And we have seen that once we have this research at universities, then we can, let's say, expect applications of some of these ideas in the, let's say, 10 years or about this time frame. What I believe that involvement of the private sector, of the companies in this research is essential, because students want to see their future career not only at universities or some research institutes. They want to see applications of their research in practice. So we need to attract those private companies to invest in this kind of research. And that's one thing I believe it's quite difficult, and it can be solved by, let's say, searching for connections and synergies with other technologies. We have heard this at the very beginning, that those microreactors and these radioisotope generators, they can be used also in other applications. And that's one thing we need to think about. That's what are the other applications of this kind of research. And really, this academic research is great for mapping different or potential technologies. We have those two directions of nuclear energy use for space exploration. Those are radioisotopes, and we clearly see really we are in a bad situation in Europe, because currently this plutonium-238, it's the only radionuclide let's say used for these space exploration missions. And once there is no, let's say, source of this plutonium from Russia, there is a clear shortage of this material, even in the United States. So we are in the position where we cannot send, let's say, European mission to space based on these radionuclides, unless we are able to provide an alternative to this plutonium-238, or starting production of our own plutonium-238 for these missions. So we need to really explore other ideas. So look for different technologies, different radionuclides, or try to improve the current technology. As we have heard, that we can think about, let's say, more effective generation of electricity from the heat of those radionuclides, which would compensate for less say power density of this americium 241. So again, this is the role of the universities, to explore the idea with, let's say, a low technology readiness level, where we can really map the situation and find some alternatives. Also, we can, let's say, focus on other technologies using those fission reactors. So, for example, we can think about using all the components of the fission power released by those fission events. So even though these are not, let's say, for immediate application, this might make Europe, let's say, a clear partner for this research in the future. And finally, what I think about is, let's say, activating the potential of the whole Europe. Really, there is a huge gap between the US and Europe. In the US, we have the private companies which are able to build reactors suitable for, let's say, installations on the moon in a few years. We are not in the position in Europe. So there's a huge gap between in these technologies, and it cannot be closed, let's say, in a few years. It's a long-term project. And on the other hand, let's not reinvent the wheel. We have the existing systems; they are working nicely, and we don't think about those radionuclides. Let's say these fission reactors; they are available, or they will be available on the market. So again, this brings me to the idea to explore the alternatives, look at new technologies which might find the application, let's say, in 10, 20 years, and which will bring us beyond the current state of the art. Because those existing nuclear power reactors, they are built on technology which was proven in the past, and their let's say, near-term deployment, it's enabled by this proven technology. So we need to think beyond. And also, we need to find those synergies between those space applications and terrestrial applications. And that's one thing which was already mentioned here, and which is really important when we think about those synergies between those space and terrestrial applications. It's the let's say, finding those common safety regulations of these installations. So if you imagine a this microreactor to be used as a terrestrial power source, and be able to transport this reactor to any site in Europe, say use it as a emergency power source in every European country. Currently, this is not possible. So we need to think about some kind of standardized designs which would be approved by all regulating offices around Europe. So this is in my perspective, is a great obstacle to applications of these nuclear technologies on Earth. So by this, I would like to conclude my speech, and thank you for your attention.
Thank you. I'm looking at time. It's 3 minutes to go, but I would like to maybe extend by 10 more minutes, so we finish 12. It's okay for you, for attendees listening us to online. I will look from time to time at Leon, who promised to follow the chats and questions coming in, also from the online attendees. But first, my question, because I understood that we have, on the one side, you can maybe, imagine a balance. On the one side, we have a issue with fuel, we have issue with funds, we have issue with framework and standardization. But on the other side, we have a technology, we have a knowledge. So what are the points missing to make this balance equal, at least to start really tackle the challenges that we have? We heard about the advisory group, what is initiated by Tractable. This is the first start. Maybe we need a European Elon Musk who will kick off everything.
Well, why not? I mean, yes, or Richard Branson, or or Jeff Bezos. It's I think at the Commission, Mr. Breton is really active in trying to create such an ecosystem. But right before, I think, I believe in a step-by-step approach. It's very difficult to in such a complex environment, and such complex also technology. I mean, the technology is there, but it's complex technology. After all, you have the saying, it's rocket science. It is a bit rocket science, even if we have the intelligence and technology and industry, etc. So step by step. So if you reach for the moon, you need to have a couple of things first arranged on Earth. And I think it starts with a strategy, and the strategy cannot be just fed by a couple of scientists or wise guys in a dark room, and they work for like 1 year, and they come up and say, well, this is it, let's go. And I think it needs a collegial effort, and also it needs to be fed by activities, because there are some trade-offs, there are some technological choices, decisions. Some options are good, some options are better, and as we said, we need a robust, resilient, and affordable. And we try to condense this to meet our ambitions. EL3, or that would be great, even if that's really ambitious. So there is also the time. Clock is ticking. That was said by numerous people. We have China, we have Russia, of course we have the US, but there are perhaps also other players, you know, we've that are eager also to put a flag on the moon. And we have those international treaties about exploiting the moon, etc. But once there's a flag, well, you know, what's going to happen? You know, it's just like in the Antarctica or in the Arctic. You know, first there, first serve, and there's a precedent. And we don't want to be, you know, the last one from the race in Europe. So my recommendation is indeed try to create this board to elaborate further on the strategy and then progressively fund, you know, some pre-feasibility studies that will feed the strategy. Because if you think of, you know, a reactor, you certainly speak of, you know, hundreds of millions of euros. And so, of course, that's a very big chunk to swallow. And they say, you know, I don't want to commit in my blood for I don't know, 500 million now. No, of course not. That's not the point. We need to progressively embark this. There are some lobbying also public saying, you know, space exploration is great. As Marcus mentioned, you know, it's not really about, at the end of the day, perhaps not budget. It's really public adherence to space exploration. Voilà, very briefly. I mean, we could talk for hours on this, but I'd like to.
Yes, thank you very much, Emilia. Domenico Rossetti, I'm the Deputy Head of Unit for Euratom Research. Thank you very much, Jan, for organizing this meeting. Thank you, Emilia and the colleagues, especially Leon, for organizing such a meeting. I'm somehow fighting to have Euratom, let's say, beyond the traditional business as usual activity that we have. You cannot imagine how sometimes it's difficult to move things in order to have Pulsar today that has been quoted 3-4 times. We had really to struggle within the colleagues, with the stakeholders, with the member states, in order to go beyond the traditional business as usual of Euratom activity. We are stretching our mandate. We are putting tension on the stakeholders, but I really feel that the cross-sectorial fertilization between nuclear and space, between nuclear and medicine, between nuclear and robotics or artificial intelligence is the way forward. I will continue to push for that. I'm sure that you will see in the next work program of Euratom Research and Training that you will have such possibility, but it's always a long fight and we need to go because the spillover effects, I think we do not speak the term spillover. It's very, very important. We need to see that as an opportunity for the nuclear with many, many other sectors. Thank you so much, Emilia.
Thank you very much. Yes.
Thank you. So I'm Gerrit. I'm one of the partners of NUCTEC, a venture capital fund in nuclear energy. My question is actually, so you ask about a new Elon Musk or a new Jeff Bezos, or so these are all actually no, these are established companies, but these started as startups actually. And in your answer, Brieux, you said yes. Commissioner Breton is really keen to see new actors coming in the field, and it's true that for when it comes to space, the space sector now is filled with startups doing small bits and pieces, but also more ambitious stuff. And so my question is would be when it comes to nuclear and space exploration, do you see startups as a piece of the puzzle? And if yes, how can we enable them to move forward in this highly complex field? Question for whoever. So Marcus, yes. Please.
Okay, thanks for the question. Simple. I've done 2 startups. You need a market. People buying from you. That's all you need. And for space exploration today, that's not there. I mean, with all respect for Elon Musk and everybody who's trying, Elon Musk makes 80% of his money from the US government. By the way, Arianespace makes only 40% of its money from government sources. Just interesting perspective here that indeed our European industry, space industry, is more private in terms of customers than the US. So that's interesting. But the startups are key. And we have to create this market, and it's going that way. We will have a lunar economy coming up. We have a Martian economy, solar system economy coming up. And that's what I was talking about previously, when we shall not deindustrialize, because that's going to kill billions of people. We shall decouple, because our economy can grow infinitively, basically, if we are not relying on material from the ecosystem. We're not extracting fossil fuels anymore. We're not dumping the waste of fossil electricity production into the atmosphere. And so we have to decouple, not deindustrialize. And that brings me to my final point in response, how the startups can play a role. Because who sets the industrial policy in Europe? That's the governments. That's the European member states' governments. They set the industrial policy. And the issue that is, and because Emilia was asking, what is the gap here? And the gap is the attention of space exploration and modern technologies on the government level. In the US, there's every month in the Congress, there's a testimony about the space policy and the industrial policy. In China, the generals report almost monthly to the highest levels of the Communist Party about the progress of the space program. And in Russia, it's a bit changing now with Rogozin. I'm not going into that, but in Europe, where is the astronauts talking to Ursula von der Leyen? Where is our space industry talking to Monsieur Macron? Well, that's happened every 6 months, perhaps. There's not enough attention on the strategic role of technology solutions like space exploration, like nuclear, like KI, AI. I'm sorry, too much German today. So where's that? It's not there, because fundamentally what happened in the 90s and millennium years was no, technology cannot be the solution. And that was, for me, that's a dead end. Technology is a solution. It's not the solution for everything, but if we give up on technology, we're going to deindustrialize. So that's just my 2 cents.
I will join 2 questions from the people in the chat. So one is Vincent Massot. He asks, should we go for European long-term program for nuclear propulsion in space? Who is to be pushing for that? Is it European Space Agency? And then is Callum Thomas asking, actually, how much would it cost?
That one I have to take, because that's programmatic. There's some programmatics involved here. Yes, we should, and we have just released, we're going to release next week an invitation to tender for nuclear propulsion technology. It's called Alumni, that's for nuclear thermal, and the other one I can't remember for nuclear electric. So we're in the process of doing that. And yes, we should, but it's underfunded because there's not enough attention from the highest levels. But I fully agree. It should cost. NASA has done that in the past. So I would think that technology development program could be in the hundreds of millions. So I would think 200 or 300 million cost at completion. So that's over the next 15 years.
Looking at the time, it's really running out. So I saw Georges van Goten from High Scientific Council of the ENS, one comment, and then a short comment from the gentleman in front.
Yeah. Thank you, Emilia. So I am a member of the High Scientific Committee, and my question is about Generation 4. Why is Generation 4 in the picture? I mean, thinking of high temperature reactors, molten salt reactors, advanced materials, new safety approach seen from all the Generation 4 people. So my question is simply, what kind of synergy could be useful with Generation 4?
Okay, I will try to answer the question, although I am also a member of the High Scientific Council. So first, you have to, I stressed that space nuclear systems, that their design has to be optimized for the minimum mass or for the highest specific power, meaning that usual technologies for nuclear like PWR, which is using light water as a coolant, so needs high pressurization, meaning heavy equipment, is of no use for space. You need to rely on either a high temperature gas coolant or liquid metal coolant. So these are typically the, I would say, the coolant technologies which is being considered and developed for generation 4 systems. So clearly, if you are thinking of generation 4 as in particular led by coolant technology, these space systems will use generation 4 technology. So I think that it is one of the key messages. And in fact, all the, for instance, the space nuclear systems which were launched in the past, either by the Russians or by the US, or which were designed or developed by the US, were using liquid metal coolant. And for space propulsion, in particular nuclear space propulsion, of course, you will use a propellant. It will not be helium, it will be hydrogen. But the fuel will be typically fuels which are being envisaged for high temperature gas-cooled reactors. And this is once more synergy, I would say, with generation 4 systems which are based on high temperature gas coolant.
Okay, thank you very much, Roland Gebel. I'm also from the European Defense Society. So it's obvious that all the scientific knowledge and the technologies are available now to develop this nuclear capability for space. What we need really is political leadership and budget. Why? Because if we compare to the United States, we had in Europe more than 40 years ago all the knowledge necessary to integrate some of these technologies in satellites. It was because of political decision that it was not made operational. In the United States, the big difference is that most of these technologies are funded by military budgets. It should be reminded that the largest space agency in the world is not NASA, it's the US Air Force. With a budget, which is now the Space Force, with the budget maybe maybe even 3 to 4 times the budget of NASA. So all these technologies were already, they developed in the 60s. And I was glad to see that the NERVA project was showed. At the end of the 60s, the nuclear reactor NERVA had a budget of $1 billion for a few, yes. And that was at the end of the 60s, which means that now you could probably multiply this by 20, which means that we need to have a much faster political reaction, and we need to have bigger budget, not to create new budgets, but to take some budget from where even defense budget could lie. This is, of course, another topic, because the lack of coordination of defense budget in Europe prevented the development of something like DARPA in the United States. And DARPA is funding many of these nuclear technologies. We need something like that in Europe. The Commission is trying, of course, with a good willingness, but with very low budget. For example, there is, and you know that probably also because they will be linked with ESA, a fund for defense in Europe, which is new, but for many years it will have 8 billion euro, which is not a lot for 8 years if you need to develop new technologies. It's a start, but we need to adjust the budget to a political willingness to make all this operational, not only for space exploration, but for strategic Earth objectives. Thank you.
Okay, we are in the end of our debate. I heard that it should be a first of series of workshops that ENS organizes focusing on space. I see the high urgency to continue the dialogue, the debate, and really involving all different stakeholders to find the perfect recipe for our European nuclear strategic plan for the space exploration. I can give it back to Carolina, the spacecraft. I think she will be happy, and maybe within the 2 decades we will develop all the elements and implement the strategy to have a strong leadership at the moon and in other parts of the terrestrial and extraterrestrial world. Thank you very much.